Okay, so here's the rest of the PowerPoint on earthquakes. So next we're going to talk about how we measure earthquakes. So intensity is one way we measure it, and that is a measure of the degree of earthquake shaking at a given locale based on the amount of damage. Most often, this is measured by the modified Mercalli intensity scale. So just to give you like kind of an idea of what this is like, kind of similar to the way we measure tornadoes, where since it's very difficult to get a measure of exactly how intense a tornado was, they basically go out afterwards and survey the damage and then decide what category of a tornado. Same thing here. They basically send somebody out, assess the damage, and then based on the damage that they see, they come up with where they think it was on the intensity scale. So that's one of the three ways that we measure earthquakes. This is a seismic intensity map of the Loma Prieta earthquake that happened in 1989. This was a particularly bad one in the San Francisco area. I always tell the story of how I remember when this one happened because it happened. I'm a big baseball fan, and this happened during the World Series. It happened actually during the pregame of one of the games of the World Series. And one of the interesting things, just as it happens to be, the two teams that were playing in the World Series that year were San Francisco and Oakland. Well, San Francisco is right here where you see the black dot, and Oakland is right on the other side of the Bay Bridge, the famous Golden Gate Bridge that's there. So it didn't matter who was home, the earthquake was there. And this is just showing you where the intensity was going out from there. And you see some kind of interesting stuff. It's not like a perfectly circular intensity map. That's because different types of geology and geography can change how the intensity varies with distance. So another way to measure earthquakes is magnitude. Most of the time for this, we use the Richter scale. And this is how most people think of measuring earthquakes. So this is based on the amplitude of the largest seismic wave. If you remember last time we talked about, and you saw the seismometer, and that this would basically measure where the highest peak was, and measure the earthquake based on that. And obviously it's named after Charles Richter. And each point on there is a 32-fold energy increase. So it's not just like a 6 is a little bit worse than a 5. It's a lot worse. So every point you go up there, it's a lot more energy that gets released. And that's basically what this is showing, just how much energy is you get based on each magnitude change. So the last one is magnitude, and we have what we call the moment magnitude scale. This is basically used to measure very large earthquakes. They basically decided that they needed something different because the other scales didn't very adequately measure very large earthquakes. And what this does, it actually determines the amount of energy based on the amount of movement of the plates. As you can imagine, if you have two plates and they move a decent amount, you can actually calculate how much energy is released by that movement just by getting the amount of mass and the amount of displacement. So that's how they do the moment magnitude scale. This chart basically just shows how many earthquakes happen every year based on magnitude. And as you can see, there are a ton of small earthquakes, 1.3 million in between 2 and 3. And then it goes down dramatically from there. If you want to pause it here and kind of take a look at this, you can kind of get a sense of like how many of each type of earthquake there are per year. Factors that determine how much damage is caused. It's caused by a bunch of different things. The intensity of the earthquakes, obviously, how long the shaking occurs, the nature of the material upon which the structure rests, so how strong it is, or if it's less strong and may like kind of shake like a bowl of jello for a while. What's the design of the structure? One of the big problems we had during the Haiti earthquake a few years back was that basically you had a whole bunch of crappy buildings there. So when they shook a little bit, they basically all came down, even though the earthquake wasn't like an 8 or a 9. I think it was in the 7 range, but because of the structures, big issues. Now you have places like San Francisco which all the buildings there are designed to withstand a certain amount of shaking. Just like here we have building codes that say we have to build for up to, I think it's category 2 hurricanes. Well, there they design for earthquakes. Destruction results from the ground shaking, obviously, liquefaction of the ground, which is where it kind of turns to like a liquid. There, the saturated material turns fluid. Underground objects may float to the surface, and you get landslides and ground subsidence, and sometimes this can even cause fire. So you have all these different things that can cause, huge amounts of destruction. Hopefully you get to kind of see that in the Japan's Killer Quake video. This is just a picture of some earthquake damage from a big earthquake in 1964 in Alaska. This is what liquefaction looks like. Once again, the video of Japan's Killer Quake also goes through this. And we also can have huge tsunamis. That's one of the big problems that comes along with it. And now we have the tsunami warning system all over the Pacific. And basically what you get is if a plate pops up, like vertically, then whatever the water that's on top of that plate will be forced to go out from there. And that's when you get that mega thrust fault that lifts and pops up, like you see in this picture down in the bottom right. That's how you get the biggest of the tsunamis anyway. And this is just showing you basically how long it takes like big tsunamis to cross the whole Pacific. Most of the earthquakes happen in a few belts, right? We have the places that are very, very prone to earthquakes. The two belts are basically the circum-Pacific belt. Circum just means circular. So basically you're talking about the ring of fire here to go all the way around the Pacific plate here. And then the other one is called the Alpine Himalayan belt, which shows over here with the yellow band, where we get lots of earthquakes there. Not that they're all there, but as you can see, there are lots of earthquakes other places too, but those are the two biggest areas where we get the most and most intense earthquakes. As far as prediction goes, for short range, there's like literally no reliable way that we can figure out where there's going to be an earthquake. Long range, however, we basically go with the idea that different regions have the likelihood of having a bad earthquake every so often. So once we know that it's been so long since an earthquake has happened in an area, then we have an idea that one is probably bound to happen there. And one other way is this seismic gap idea, which is basically, if you look at this picture, you see where the earthquakes happened. 2004, you had one up there, 2005 down there, 2007, 2000. So you've had all of these big earthquakes along this fault over the last 20 years, but there's one place that hasn't had one. Well, that basically tells us, we're probably going to have one there soon. So you can kind of, not that you can really prepare, but you can have some preparedness. We also look at paleoseismology, which is basically like historical seismology, where we look at what's happened over what kind of range and get an idea from that. Most of our knowledge of the Earth's interior comes from PNS waves. I think we talked about this a little bit back when we talked about the interior structure of the Earth. But we look at the way the P waves and the S waves travel through the Earth, and we notice that S waves travel only through solids. And that basically tells us that there is a liquid part to the interior of the Earth. And that's what this shows two things. It shows some waves can't get through. And it also shows that you get bending, so refraction of some of the waves. And that refraction will vary depending on the type of material that the wave goes through. So we can get density calculations from the refraction of the waves. And then this is just a, quick, this is what the Earth's layers are. We kind of already talked about all this stuff. So we'll kind of skip through this since we already talked about it. All right, so that's it for Chapter 8.